Welcome back. In this part of the talk, we'll discuss about the atmospheric aerosols and what contribution atmospheric aerosol has in the climate change and other perspective. What are the radiation forcing and the aerosol radiative forcing aspects? So these things we'll discuss in in this lecture. So to start, uh, we can see that there are two, we can say, grand challenges which are there in terms of climate change and say pollution. One of them is the air pollutants, and the other is the greenhouse gases. As we have seen that these two are the major contributors in the climate change. Air pollutants, various air pollutants which degrade the air quality, which eventually affects our health and other climatic parameters also. And then there are greenhouse gases like carbon dioxide, methane, nitrous oxide, and others. So we have already seen that over the last about a century and a half, the concentration of these greenhouse gases have increased tremendously, and it is leading to an increase in global warming. The average mean temperature of the land and ocean both are increasing because of the increase in greenhouse gases. But another culprit, which is the air pollutants, and which are coming from different sources, they can be in the form of particles, in the form of trace gases, and other gaseous contributions, including the greenhouse gas production that is taking place. So these are contributing towards the climate change. Now these health implications, it has been projected by several agencies, including the World Health Organizations. There are several diseases, but briefly, just the mainly it is impacting our heart, lungs, and other respiratory systems. Then it also increases the chances of cancer, nervous breakdowns, and all these things are related with the effect of pollutions. And practically, we can see that when we collect these particulate matters, particularly over a clean filter, the left one, which is showing the white clean filter, and just after 24 hour uh, uh, collection of these aerosols, particularly the PM10, over this filter at a rate of say about 16 liter per minute, then we can see how black these filters become, which is an indication that how much black carbon or the pollutants we are breathing in a polluted environment. So these are the various health implications and various effects. So various sources in the of the aerosols, they can be categorized in the form of natural and anthropogenic. The natural aerosols, as we know, are the wind-blown dust, whether they are sea sprays or volcanic flux, which is coming out, and the forest fires, which contribute to sometimes natural aerosols also. Then pollens, vegetation, and even the meteoritic debris, and then the various reactions from natural gases which are occurring in the forest, and then the small particle formation. They are all part of natural aerosols which are produced in the atmosphere. But apart from that, there are various anthropogenic contributions from the man-made activities which contribute to the aerosols, and they are, say, for example, the industrial and mining activities which contribute to it. Then transport is a major sector which contributes huge amount of aerosols in the atmosphere. Then fossil fuel and biomass burning, shifting cultivation, and then clearing of cultivated waste. Then urbanization, of course, is another important thing which contributes to aerosol production. So there are various sources of these aerosols which are going into the atmosphere, and they can be sometimes divided into the primary and the secondary aerosols. Primary aerosols are those which are introduced directly into the atmosphere, for example, smoke or from the combustion. So these are the primary particles which directly in the form of particles they contribute in the atmosphere. Then there are secondary particles. Sorry. So these secondary particles are formed because of the chemical reactions in the atmosphere, and say mainly from the gas to particle conversion. So they are also a source, a very major source of atmospheric aerosols. Then, of course, there is another categorization of natural aerosols and anthropogenic aerosols that we have already seen. About 60 to 65% of aerosols are natural, but around say 35 to 40% sometimes aerosols are due to anthropogenic origin. Now these aerosols which originate from different processes, whether it is from gas to molecule conversion or from condensation of very small particles or which are called the nucleation, very small particles around which the other particles or moisture can be accumulated. So those are the small size particles of the range of 0.01 micrometer. So these are the also the nucleated particles, or sometimes they are also formed because of condensation. And after that, some sticking together of particles takes place, which is called the coagulation. So this is also a major source of atmospheric aerosols, which in the form of coagulated particles, they increase the size of the particle in the atmosphere, and they remain there for quite some time. Then so these are the various processes through which the new particle formation or the particles which are already existing in the atmosphere, they grow in size, and they are eventually staying in the atmosphere, having different sizes, starting from the very minute size of nanometers up to the range of almost 10 micrometers. Now, these particles sometimes they are also divided in terms of different modes of the particles, which are Atkin mode. Say, for example, it is ranging from 0.001 to zero point 0.1 micron. Then accumulation mode, which is usually zero point 0.1 to 1 micron in diameter. Then, of course, there are coarse particles, which are large particles in the atmosphere, say, particularly from, say, dust storm or other accumulation of particles, which can be generally greater than 1 micrometer size in the atmosphere. And then there is a nucleation mode, which is again a very small size of particles which are existing in the atmosphere. Now, they can have different distribution kind of thing depending upon their sizes. So these distributions can be volume distribution, can be number size distribution, and other kind of distributions in the atmosphere uh, for different kind of sources of particles. So eventually, all these different sources, they have their own size distribution, and finally they contribute to a larger size distribution in the form of coarse mode and fine mode of the particles. Now, why studying these particles are so important? Because they have different effects. So first we can see some of the uh, non-climatic effects, which include the air pollution, as we have seen earlier, which have health effects, which can have on the scale of local, regional, or global scale. And then they also affect the fertilization of the global ocean. They have effects on, say, for example, the dust which is originating at one place, they can travel to the longer distances, and they can eventually get accumulated at the sea surface, increasing the iron flux from desert dust to other sources. So they change the fertilization of global ocean also. Then they also cause attenuation in the ultraviolet radiation, UVA and UVB particularly, which will again have impact on the fertilization of global ocean. Then, of course, they also impact the tropospheric chemistry and photochemistry of the atmosphere, where the different kind of atmospheric particles with the different chemical characteristics, they interact with each other, and then eventually they change the photochemistry in the atmosphere. That is, they have different effect on the different kind of radiations ranges in the atmosphere. Apart from that, they sometimes also affect the our remote sensing observations, because these aerosol particles they affect the because they affect the source of radiation which are used in case of the satellite based measurements, and because of these small particles, sometimes these observations are also affected. They also in turn change the sulfur surface albedo or atmospheric ozone and other things existing in the atmosphere. So these are some of the non-climatic related effect that aerosols have. But mainly we will concentrate on the climatic effect of these aerosols. And here the aerosols are by and large, if we take the global average, then on the whole, they actually cause the global dimming. That is, they basically reduce the net amount of radiation which is reaching the surface. So, and the average estimates go up to, say, the mean radiative forcing, what we call. We'll see what is radiative forcing in the coming slides. So they change the mean radiative forcing of the atmosphere by almost they reduce it by around 2.8 watt per meter square, as we'll see later. Now these aerosol particles, they affect the radiation through aerosol radiation interaction in several different ways, and the most common way is the direct effect, in which these particles are absorbed. These aerosol particles absorb solar radiation, and they also scatter the solar radiation. So through the process of scattering and absorption, they directly affect the radiation which is coming from the sun and reaching at the surface. Say these, and that is why it is the surface cooling by the scattering of usually takes place in the short wave range. So these short wave, they are also called the short wave surface cooling of atmosphere due to aerosols. Similarly, there are some particles like soot or dust which can absorb the solar radiation. They actually increase the atmospheric temperature by absorbing the solar radiation in different wavelength bands, uh, and they create heating due to absorption and contribute into and then they change the atmospheric circulation. But then there are other effects which are called semi-direct or indirect effect. For example, in the indirect effect, the particles, very small size particles, if they reach the cloud heights, then they change what is called the cloud condensation nuclei. Now, these are the small particles over which the nucleation of water molecules takes place, so that inside the cloud, and when these sizes increase by sufficient size, then eventually the rain takes place. So it is the cloud condensation nuclei are the essential part of you can say aerosols, which are helpful in producing rain. Suppose there are no cloud condensation nuclei, then there will be no rain, because although there will be water vapor around, but they cannot accumulate on, they need some particle on which they can accumulate initially, and then they will grow in size for accumulation of more water vapor, and finally it will become a drop and fall down as rain. So so this way, they indirectly, these aerosols affect the climate, and it is called the indirect effect, or also called sometimes the Tommy effect, because Tommy was the scientist who first studied this effect of cloud condensation nuclei, and showed that how an increase in number of cloud condensation nuclei will change the rate of rainfall, and so on and so forth. Then there are another effect which are called the second indirect effect, which may be when these particles reaches the cloud height, and then because of the number of particles which increase inside the cloud, then they will change the cloud albedo. So by changing cloud albedo, albedo is nothing but it is the ratio of amount of radiation which is reflected to the total amount of radiation which is received. So if the number of particles, they also change the albedo of the cloud, and they cause the secondary indirect effect, because now the cloud may become more reflective, for example. On the other hand, if those aerosols are absorbing in nature, then inside the cloud there will be more absorption of radiation. So the whole cloud will kind of burn off, like it will be heated from inside because of these minute particles, and because of that heating, the cloud burn off effect will take place, and so the eventually the it will affect the rainfall. So these are the processes by which the aerosols they affect the climate in a very long way. Now, some of the important properties of these aerosols, which we need to study in order to study the climatic changes or even the non-climatic changes, and they are, say, the number size distribution, their altitude profile, their chemical composition, even the refractive index of these aerosols, which eventually decides whether the particle is more absorbing or more scattering. Then the various radiative properties of these aerosols, which are important, for example, the spectral optical depth, single scattering albedo, then the scattering phase function, symmetry parameters. So all these are technical terms which are actually denoting the various properties of these aerosols, which need to be studied while doing any kind of study on radiative transfer, or the radiative forcing measurements, or eventually for any climatic modeling studies. So now, because we know from the fundamentals of physics that the interaction of solar radiation with atmospheric aerosol can take place in any of these four processes. Say it can be absorption, can be reflection, can be scattering, and then it can be radiation processes by which the aerosol radiation interaction takes place, and it affects the overall radiation budget. So we are aware of most of it, but a little bit about the scattering, because scattering, is nothing but a redistribution of energy. When some energy, some radiation is falling on a particle, which absorbs it, and then it re-radiates it in various forms. And then this re-radiation not necessarily is taking place in the forward direction, but in various other directions with varying intensities. And that is why this scattering is an important process, which is uh, important for the aerosol studies, particularly when we study the aerosol radiation interaction parameters. Now, these scattering, as we know from the atmospheric point of view, can be mainly of two types. It can be relay scattering or Mie scattering. When the particle size is very, very small, then in that case, the scattering is almost homogeneous in different direction, and in that sense, the it is in forward and backward direction. It is normally equally distributed. So, but these are for the particles which are very small in size, say particularly you can say the gaseous particles which cause these relay scattering, because gas eventually they are also the particles, and they are scattering the radiation. When these particles are comparable with the wavelength of the radiation which is falling on it, that is not very large in the size, but of a moderate size, say particularly in the range of a few micrometer, then in that case the scattering which takes place is called the Mie scattering. And then in Mie scattering, the important thing is that the scattering is not uniform in all the directions, but in the forward direction, the scattering is maximum. The maximum energy is contained in the forward direction, but the scattering is eventually taking place in different angles, and which is not uniform, as you can see from this picture. So, and then when of course when the particle size becomes very large, then in that case the normal geometric optics takes place, and then uh, the ray optics which we study, it is particularly when these particle sizes are in the range of optical regime. Now, these particles, as we have seen, they can have different refractive indexes, and all the particles, basically, all this radiation interaction takes place because of the refractive index, which can be real, which can have two parts, real and imaginary. The real part of the refractive index is basically responsible for the scattering of radiation, and the absorbing part is responsible for the absorption of radiation. So you can say in case of say some of the particles which are basically more of the scatterers, like sodium chloride particles, which are from the sea salt origin, or the H2SO4 in the atmosphere, or the other sulfates in the atmosphere, then silica, so silicon oxide. So these are the particles which are mainly scattering. They will have the refractive index, which has a large real part of the refractive index, and the very small or no imaginary refractive index, so that they are not absorbing. But the particles like black carbon, or say dust from mineral sources, or mineral dust, what we can say, or desert dust particles, sometimes they have the imaginary refractive part also, and they are large enough to cause strong absorption, particularly in case of black carbon, which is nothing but uh, the particles which are not fully on which the combustions has not taken place completely. So those are the particles which will form black carbon or soot in the atmosphere. Now, various parameters that we just listed earlier, there are processes of finding those parameters, and there is a particular definition for that. Say, for example, the aerosol optical depth is the net extinction of radiation which is falling in on the atmosphere. So extinction is nothing but total of scattering plus absorption. So the net effect is that eventually it will reduce the amount of radiation which is falling on the surface, and if we integrate the total amount of extinction in a pathway which is having say a number of particles, then the net then the net extinction can be measured in terms of what we call the aerosol optical depth. So it basically it varies under different conditions. For example, and then at various locations, their variation will be different. And these aerosol optical depth is also a function of wavelength, because as the wavelength increases, the aerosol optical depth normally decreases, except under certain circumstances when it may be constant or even it can increase. But usually with the wavelength, the aerosol optical depth decreases. So then these, say for example here, this is a typical example from Delhi, where we have measurement of aerosol optical depth at on different days. Particularly during the dust storm days, you can see that the aerosol optical depth is, instead of decreasing, it is either constant or sometimes even it increases with respect to wavelength. So in this case, it really doesn't follow the angstrom formula, what we can say. Otherwise, the aerosol optical depth and the wavelength, they are related by what is called angstrom formula. Tau is equal to beta lambda to the power minus alpha, and then these alpha and beta, they are various. They are called angstrom exponents. If you can see when alpha basically indicates the size distribution of the aerosols, how in the atmosphere the aerosols are distributed for different diameters. And then beta is nothing but it says the what is the amount of aerosol in the atmosphere, or you can say the what is the turbidity of the atmosphere. So how dirty the atmosphere is, that will be determined by beta. Now these are the some of the parameters which are used to study the different kind of aerosols in different modes. For example, when alpha value is greater than 1, then in that case the fine mode particles will dominate more. Here, if this is the kind of distribution that we consider, then this is the fine mode which is dominating here. If both fine and coarse mode are of equal amount, then the alpha will be 1. And once the coarse mode is dominating, then in that case alpha will be negative. So this is what is observed, where here in this case, during the dust storm, you can say this is a typical case of dust storm which occurred over Delhi. So when there is very high concentration of coarse mode particles which are coming because of dust storm, then in this case alpha is actually less than 0 also. So these are the typical cases in which these angstrom exponent will have different behavior. But overall, depending upon the different kind of sources, it is not necessary that the atmospheric aerosol will have only two modes, fine and coarse mode. There can be various modes possible in the atmosphere, and in fact in actual atmosphere there are multi modes of aerosols present in the atmosphere, and the distribution is actually multimodal as shown here. Then the other parameters like single scattering albedo, it is nothing but the ratio of scattering to the total extinction, and it is a very important parameter when we study the interaction of aerosol with radiation or radiation forcing. The another important parameter is the asymmetry parameter, which is nothing but the average of cosine of a scattering angle for all the scattered radiation in all the directions. And this very strongly depends upon the shape of the particle, and it affects the aerosol radiation interaction. So these are various numbers for say, the single scattering albedo. It varies for different kind of particles because these particles will have different kind of chemical structure. So depending upon that, say dust will have single scattering albedo of 0.8. Sea salt, which is completely scattering, will have single scattering albedo close to 1, and so on and so forth. The black carbon, which is very strong, it will have a very strong absorption, so it will have very low single scattering albedo of the order of 0.2, and so